Good day, everyone. My name is Eliza Sarai Arenas, and I'm here to discuss with you my thesis entitled The Effects of Polyethylene Glycol Methacrylate Compatibilizer to the Mechanical Properties and Morphology of Husk-Filled High-Density Polyethylene Composites with the help of my thesis advisor, Ms. Chelsea May Alice Kutum. So the significance of the study, of course, to produce a high-density polyethylene composite which is more efficient, eco-friendly, low-cost, that may benefit future researchers since I think this type of topic would be beneficial in the research world in general, since polymers and abundant agricultural waste are both discussed. And of course, the environment and even the farmers, since the farmers may make a business out of the rice husk, and then to also introduce polyethylene glycol methacrylate or PEGMA as a promising compatibilizer. So for the objectives of the study, its main objective is to examine the efficiency of using PEGMA and rice husks as fillers in the fabrication of high-density polyethylene composites in terms of its mechanical properties and morphology. So for the scope and delimitation, the only matrix to be used is high-density polyethylene and not other types of polyethylene and polymers. Its reinforcement filler is rice husks, and it is not the sole material of the production. The compatibilizer will be polyethylene glycol methacrylate or PEGMA, and the only properties to be discussed would be mechanical properties and morphology. So for the methodology, the matrix to be used is high-density polyethylene or HDPE, and the form or the type that I've used is the plastic labo sheets, specifically the Calypso ones, 8 by 11 size, and we'll also use the filler rice husk, which was ground and sieved. Then the compatibilizer to be used is the polyethylene glycol methacrylate or PEGMA. So to produce these composites, these three materials were put under the two-roll machine, then compressed in the compression molding. Then for the characterization, it was put under the UTM characterization for both tensile and flexural properties, and a digital microscope was used to study its morphology. Then this is a ratio of the composition per sample. This is a picture of the samples produced. This summarizes the tensile properties, specifically the tensile strength, tensile stress at break, and tensile stress at field in relation to the increase in the filler loading and compatibilizer. So as you can see here, there was a sudden decrease in tensile strength as sample code 1 upon the introduction of the rice husk. This could be explained by the fact that rice husk is naturally hydrophilic or water-loving, then HDPE is a naturally partially hydrophobic or water-fearing. Thus, it would be understandable if they have poor interfacial adhesion, especially without the presence of the compatibilizer. But as soon as the compatibilizer is introduced in sample code 2, there is an increase in the tensile strength and caused by the betterment of the interfacial adhesion between the two materials. This is because upon the addition of the compatibilizer, there is equal distribution of the stress between the filler and the HDPE matrix. This is also applicable to sample code number 3. However, in sample code number 4, there will be a decrease since sample code number 4 does not have the compatibilizer, and instead there is an increase in the rice husk. Then for sample number 5, there is an observable increase with the introduction of the compatibilizer once again. And for sample code number 6, it is quite different with the expected trend. And I will discuss this later on in the morphology part. The tensile stress of break is quite similar with the trend in the tensile strength since they are quite related with one another. So as the rice husk introduces moisture to the material, it results to the weaker interfacial adhesion, thus lower the tensile stress break. And on the other hand, the addition of the compatibilizer improves this interfacial adhesion and prevents the material from rupturing easily, thus improving the tensile stress at break. And as you can see here, the tensile stress yield does not have any values for the other samples aside from sample code 0. From the UTM test results, the other samples have no values obtained. And as we know, a yield point is a stress point beyond the elastic limit of material at which this material begins to deform or exhibit plastic properties. So since the remaining samples did not deform and slowly proceeded to the break, thus the requirement of the tensile stress at break of these samples. So as you can see here, again, the only percent elongation at yield obtained was from sample pool number 0, with a similar reasoning with that of the tensile stress at yield. There might have been no plastic deformation and just proceeded with break. And for elongation at break, there was no value obtained for sample code number 0. This elongation at break could be supported by that the weaker interfacial regions give way to cracks and fractures of composites that occur at lower values of elongation. And in terms of addition of the compatibilizers, it is expected that the compatibilizer would delay the rupture or breakage of the material since it helps distribute the stress evenly in the material. And in terms of the Young's modulus or modulus of elasticity, it is a common result that as the filler loading increases, the Young's modulus of the composite increases as well. And because compatibilizers improve the interfacial adhesion between the filler and the matrix, it results to a higher surface area and thus increased modulus of elasticity for the material. And in fact, modulus is generally dependent on the filler content in composites rather than the compatibilizer. Thus, minimal increase in the flexural modulus upon the addition of the compatibilizer. Next would be the flexural properties, specifically the flexural strength, flexural stress at a given strain, and flexural stress at break. So as you can see here, there is quite an opposite effect with the tensile strength. Since upon the addition of stress has, there was an increase in both the values of the flexural strength and flexural stress. This could be supported by the fact that rather than the interlaminar shear, the breaking of the fibers accompanies the flexural strength. Although tensile strength and flexural strength both pertains to the material's resistance to load, they differ at the position at which the loads are applied. So once the material is bent, the extreme fibers experience the largest stress, and if these fibers are intact and free from defects, the flexural strength would be controlled by those fibers. However, once subjected with the tensile stress, the fibers experience the same stress all throughout, and once the weakest fibers reaches its limit in tensile stress, failure can occur. Thus, the difference between the effect of the addition of rice husk in the tensile strength and the flexural strength. And of course, in general, the addition of the compatibilizer would mean greater interfacial adhesion and higher flexural strength. Then we also have the flexural stress. Actually, the results given were that of 3.5% and 5%. However, for the 5%, no values were obtained. This is similar to the reasoning for the pressed properties with no values obtained. For the flexural stress at a given strain, the flexural stress at a given strain or the maximum flexural stress at any given strain is similar to the flexural strength in general. However, the difference is that it is not necessarily the maximum point that the material could reach, but simply the flexural stress or resistance at a certain point. Thus, it is expected that the values obtained of flexural stress at 3.5% strain has the same trend as that of the flexural strength. And as you can see here, the flexural stress at break also do not have any values. Similar with the reasoning with the flexural stress at a given strain, 5%. And the elongation at yield. Next would be the flexural modulus or the flexural properties. And as what I've said earlier, the modulus is not quite dependent with the compatibilizer and dependent on the rest husk. So flexural modulus, on the other hand, pertains to a measure of the stiffness or resistance to bend of a material when force is applied to the sample's wrong edges. So it was observed that the composite increases its stiffness as the filler loading increases, or in other terms, there is an increase in the flexural modulus with an increase in the filler loading. So I will not dwell too much on the sample code 0. Instead, I focus on sample 1, sample 2, 3, 4, 5, and 6. So from the table before, sample 1 is the composite with 45 grams of rice husk. Sample 2 also has the 45-gram rice husk, but with the introduction of the compatibilizer. And sample 3 also has 45 grams of rice husk, but with even more compatibilizer than sample code number 2. Then sample 4, 5, 6 has 75 grams of rice husk, and from left to right also has increasing number of compatibilizers. So as seen in sample 1, you can see that there is poor interfacial adhesion between the rice husk and the HDPE composites as represented by the color whitish area. And we can see strands of the HDPE. Then for sample code number 2, we can say that there is a better interfacial adhesion between the two materials. And for sample code number 3, there is even a better interfacial adhesion with less visible strands of the HDPE. Then for sample code number 4, again with the absence of the compatibilizer, there is an expected poor interfacial adhesion between the materials. Then, as you can see in sample 5, there is an improvement in interfacial adhesion. And for sample code number 6, as what I've said earlier on, there is a sudden decrease or an increase in the sample code number 6, which is different from the expected trend. And it could be supported by the fact that sample code number 6, there might have been errors in its fabrication, since even with the addition of the compatibilizer, there is still a quite poor interfacial adhesion as compared with that of sample code number 5. And there is an even distribution of the HDPE, since there is an accumulation of the whitish area in the lower left part of the figure. So basically, the increase and decrease in the tensile and flexural properties in general of the composites could be explained by their interfacial adhesion. So as we said earlier, great interfacial adhesion means that there is even distribution of the stress between the rice husk and the HCP. So to conclude, compatibilizers really help improve the interfacial adhesion of composites, but it is important to identify or explore the structure of this compatibilizer and the filler and the matrix in order to determine if they really are compatible with one another. Then, in terms of studying the mechanical properties of the materials, it would be great if the morphology could also be discussed, since since this would be of great help to support the claims of the results from the mechanical properties, since they are related with one another. Then, for the recommendation for further study, first use other compatibilizers, since we've only used the PEGMA compatibilizer. Then collect rice husk from different locations, since I've only collected rice husk from San Juan, Batangas. And I think different locations would provide different type of rice husks and vary mixed ratio of the raw materials, and explore other characterization techniques other than mechanical properties and morphology, and also even discuss the impact impact strength, and the toughness. So thank you very much for listening and have a great day. Stay safe.